So now I want to talk about our what are called estimation problems. And the setup is pretty simple. So I'm given a value of a random variable y that I observed. I want to find the best estimate of some corresponding or some correlated random variable x. Okay, and these kinds of problems are kind of pervasive in electrical engineering and science in general. Basically, it is I have some sort of underlying random variable that gets put through some sort of a process or a system. In electrical engineering, a lot of times you see this in the context of a communications channel, right? X is the bit that goes into the channel. It gets maybe noised up, and what comes out is some random variable y that is no longer 1 or 0, but instead it's a continuous number, for example. And so then what I want to do is I want to process what I saw with what I would call an estimator, which produces for me another number, x hat, which is an estimate that I get by applying some deterministic function to y. Okay, so I see y, I do something to it, and now I have the best estimate of x that I can make. And so this concept of best varies according to different definitions of optimal, right? So the one I want to talk about in this lesson, and we'll go on to other ones in the next ones, the first one I want to talk about is called map estimation. And this stands for maximum a posteriori. So the philosophy behind map estimation is simple. It basically says, given the value of y, what value of x is most likely to have occurred? Okay? And saying this in a different way is we're going to use the conditional probabilities that we kind of talked about a while back. The estimate I'm going to get is a function of y, g sub map, and that is going to be the x that gives me the maximum conditional probability x given y, right? I tell you y, it makes sense that what I want to do is find the correspondingly maximizing x given that I know y happened, right? And so to draw a little picture, this is just like saying I give you y, that means that I produce then a new PDF on x, which is some new PDF, and the map estimate is basically the value of x that maximizes this PDF. This is going to be my GMap, okay? And this is the way it works. So let me, to make this concrete, go back to our coin flipping example, right? So I had this example that I used several times before. The idea is I flip a coin 3 times, and I let x be the number of heads, and I let y be the position of the first head, okay? And so you can see here that basically I have 3 or 4 possible values for x. Let me move this back like this. And then I have 4 possible values of y, and these are the joint probabilities in the table, and then these are the marginals that I get from adding down the columns and adding across the rows, right? So hopefully this is a familiar example if you've watched previous lessons, okay? So now I want to know the conditional probability x given y. What that says is, okay, I give you y, and then what I should do is I should normalize along a given column to produce a new PDF that's in x alone, right? So if I were to do that in this example, that would be like saying, okay, here are the columns of y. And then I would say, okay, so now that I've normalized along these columns, I choose a value of x that maximizes the corresponding conditional PMF. And so in this case, I can kind of read them off just by looking at them. So the maximum in this column is this. The maximum in this column is this. The maximum in this column is this. And the maximum here is kind of a toss-up. It doesn't really matter. I can choose either one of these things. So if I want to be, concrete, what I would say would be that the GMap estimate of y depends on what y is, right? So if y equals 0, y equals 1, y equals 2, y equals 3. If I look back at this, this would be like saying, well, if y was equal to 0, I should choose x equals 0. If y was equal to 1, I should choose x equals 2, and so on. So let me just write down what we learned from the previous picture. Here, basically, I could choose either 1 or 2. It doesn't really matter. So I can just say, okay, flip a coin between 1 or 2. And this would be 1. Okay? And then I can compute the probability of making a mistake. with this estimate, right? Because clearly, go back to this. So if y is 0 or if y is 3, then I'm never going to make a mistake because there's only one possible value of x. If y is 1 or 2, then I have some non-zero probability of making a mistake, right? So I can compute what that is, and I can use the law of total probability to say it's basically the sum of the probability of error given that y is equal to k times the underlying probability that y is equal to k, which I can get from the marginal that I already know, right? And so in this case, that's like saying, well, I have 0 probability of error if I'm in the y equals 0 case. I have 1/2 probability of error if I'm in the y equals 1 case, and that had probability y equals 1. I have basically 1/2 probability error if I'm in the y equals 2 case, which had probability of 1/4, and I have 0 probability of error if I'm in the y equals 3 case. So I can add this up and I get 0, 0, 1/4, and 1/8. So the total probability of error here is 3/8. Okay, so that's the map estimate in this discrete case. To do a continuous example, what I could say is something like, remember the jointly Gaussian random variable. Right? So if I have 0 means and standard deviation is equal to 1 and some non-zero correlation coefficient, then what we found out was that f of x given y was Gaussian with mean rho y and standard deviation this. Okay, so we don't really care about the standard deviation. All I care about is that I've got a Gaussian, and the center of the Gaussian is at rho y. So that would tell me that if I tell you y, then rho y is the location on the x-axis that maximizes the conditional probability, right? So that's pretty easy to do just from looking at it. The problem with all this is that a lot of times we don't know x given y, right? It's more likely that we know y given x, right? So let me just say for a second that that's why we have other ways of doing estimation. So we may not know or be able to obtain a good estimate of this class conditional probability. Usually it's the other way around. Usually what we have is f of y given x, right? And that's true because, for example, let's suppose I have my communications channel. What I could do is I could just put a whole bunch of x's through the channel and then look at the y's that come out, and I know, okay, if x went in, this is the y that I saw. So this is really what I'm getting by doing this experiment where I have access to the physical system, right? Now, even if I had this, what I could do is I could say, well, okay, I could get this by doing Bayes' rule, right? So I know that this is true, right? This is basically Bayes' rule, or if I move this over, I can get the joint. So this is kind of something where I could say, okay, well, I could observe this, and I could, measure this also at the endpoint. And this is okay if I know during my testing process, right? So, I mean, when I'm allowed to touch the channel, I know what the distribution of x is also. But the problem is that in the real world, I don't really know what the distribution of x is. If I did, I wouldn't really have this problem, right? So this is the tricky part, is that, in the real world, I don't know what the distribution of the data is, right? All I do is I see how the system has acted on this underlying true data. And so what we're going to talk about next lesson is called maximum likely estimation, which kind of gets around this problem when you don't have a good estimate of the distribution of x.